host is going to introduce Richard Alley.
What the heck is up with Richard Alley? We have a lot of people in this room that know how to give a talk, that know when a good talk occurs. But you know, Richard Alley, he doesn't exactly give a talk so much as open up a new Disney theme park. Or maybe a scene from a new Indiana Jones movie. Well, it'll start off innocuously enough with some sort of reference to history, some important episode, Gardy Lou or something like that. And then the turbo will kick in. You know, references to papers rattled off like an auctioneer, acknowledgments of audience members like prizes at an Oprah Winfrey show, and a careening course through a slalom run of ideas to get to the goal. World peace. Maybe a theory of everything, or maybe just a settled sense of a problem well grasped. The key thing about a talk by Richard Alley, it makes everyone in the room feel like they're brilliant also, and like we all arrived at the conclusion together. Dr. Richard Alley, the Pew Professor of Geosciences at Penn State University, will speak to us today regarding crumbling ice cliffs, not so good news for low coasts. Or, if I may subtitle, if the cliffs get high, head where it's dry. Dr. Richard Alley.
Oh dear, thank you. Oh my goodness, what do you do after that one? Okay, so thank you. Ted is brilliant, so that makes it easy. And it's just, you know, it is refreshing to come out here. Aside from the beautiful morning and the Flatirons right up there, but it's refreshing to come out here and look around this room at just the amount of brain power that is running here. It's just truly amazing. And I was standing back there learning more things in shorter time than you can possibly imagine. So this is great. So thank you for inviting me. I'm in town for the CWA. If anyone can explain this thing to me later, I'd be happy to hear it. Okay? I'm trying to figure it out, but we'll see what we can do. And this is an update because some of you heard part of this 2 or 3 years ago. But in some horrible sense, I've been giving this talk my whole career. And the history, I'm going to do the history here, right? So the history is, look, I'm getting old. I know I'm gray and what, but you know, this is the Hero. I went to Antarctica the first time in 1978 on the Hero. I threw up all over that boat. Okay, and I have been doing glaciology since 1977, right? I started in Ohio State in the fall of '76, and Ian Willens hired me the next summer to do radar records. Some of you are still working on those dead blame things, okay? And so this is yours truly in 1977. So I've been working on this problem for almost 38 years because this is the Bird Station Strain Network. So we were doing West Antarctic stability, we were doing sea level rise, we were doing what John Mercer told us to do 38 years ago. And you know, I always believed exactly what it says here, that we would learn enough, that we would be useful to society before it was too late. And you know, if you missed this paper, you probably shouldn't. But Ian Jockin here, marine ice sheet collapse potentially underway for the Thwaites Glacier Basin in West Antarctica. You know, our simulations provide strong evidence the process of marine ice sheet destabilization is already underway on Thwaites Glacier. And you know, did we blow it? Did we take John Mercer's knowledge and fail to use it? And it's one of those questions that I'll bet you that Ted looks at the mirror in the morning and asks the same question that I do. Because he hasn't been doing it as long as I have, but he's not that far short of it, okay? So this question of, we knew in '68, John Mercer says, you know, West Antarctica is a worry for sea level rise, and we've been working on it since then. And did we screw up? And it's a very good question. Now, remember, the marine parts of West Antarctica are only 3.3 meters of sea level rise, but unfortunately that's globally averaged, and you'd get 4 or a little more up in the northern hemisphere where most of the coastal people live. So this is not yet the end of the world screaming hairy disaster conniption fit, but 4 meters of sea level is still a big stinking deal. And that's 4 meters of sea level plus thermal expansion, plus mountain glaciers, and plus this little ice cube in the north called Greenland that might be melting on top too. And we'll come back to East Antarctica because there's a little of that. So at any rate, in case you haven't run into this one, most of you know this really well, but if you haven't come into this one on why the Northern Hemisphere gets screwed more by West Antarctica than anybody else does, it's this business of West Antarctica is so important that it pulls the ocean to it. And when you melt the ice sheet, the water rises, but then the gravitational attraction relaxes, and in the near field, actually sea level falls a little bit, which is one reason why melting ice sheets and sea level's not really controlling the ice sheets, it's other things, but in the far field you get extra. And so 4 meters up here or something like that, plus all these other things are in play if Ian Jochen is right, okay? Some of you have seen these slides before. I'll do the tiny little bit of glacier physics here. If you make a pile, it spreads. Thank you. It doesn't spread if it's really strong, so the building is not falling down, and it doesn't spread if it's got lots of friction underneath it, and it doesn't spread if you hold it in. And that's basically all the physics you really need to be a glaciologist, is piles spread under their own weight. And this was, this building is not falling down, but these people actually discovered that if you built too big of a beautiful building, it did. The walls would bulge out and the roof would cave in, and so they invented these flying buttresses to keep from losing their Gothic cathedrals. And so there's your physics of ice flow. And an ice sheet, right, is a 2-mile thick, 1 continent wide pile of old snow. It spreads under its own weight. Snow on top builds it up, melting on the sides or breaking off to make icebergs on the side makes it smaller, and it balances the snow on top with the spreading and the loss on the edges. And because the ocean gave it the water, it changes matter. So there's the physics. And what we tend to focus on recently is this business of the flying buttresses of the ice sheets. If you are doing Greenland, up here might get warm enough that it melts. If you're doing Antarctica, if we get to that, so many other things have gone wrong that we're probably not worrying about that anymore, okay? So if we actually get it hot enough that Antarctica is melting up there, we're in really, really, really deep doo-doo. But we are worried about this one because even if this is minus 50, this is at the melting point and this is close to the melting point. And so because the flying buttress here has friction with these pinning points and with the sides, anything that happens underneath that is a big deal for it. You get it out of the way, you lose the friction, the pile spreads faster, and that raises sea level. And so the Antarctic is warming. I have a gratuitous penguin picture here, and here are a whole bunch of gratuitous penguins. And the penguins actually, as you probably know, they don't sweat. So when they get hot, they put their feet in the water to cool off. And here are lots of them with their feet in the water cooling off. And in 1980, the glacier was down there a mile away, and now the glacier is up here because it's melting back. Okay, this is one place, one glacier doesn't prove anything, but lots of the subantarctic is doing this, lots of the regions around Antarctica are doing this. And very broadly, so here's Eric Steig's paper, this is temperature trends, and yes, there's a lot of warming going on here. That matters, it's not the biggest thing will be the ocean, we'll come back to that. But is there warming in the Antarctic? Yeah, there really is. And then Ted has worked extensively on this one, but he could narrate these pictures better than I can, but at any rate, if you remember this story, we are here at the tip of the Antarctic Peninsula, and this picture is rotated slightly, so this is the mountain range that's the Antarctic Peninsula, and the glacier's just dripping off of it down to the ocean. Black is ocean over here. The scale there is 20K, 12 miles, so these little icebergs are bigger than aircraft carriers. And this is a whole bunch of meltwater sitting in ponds on the surface of the ice shelf because warming is making more melt. And if you put water in the crack, it tends to wedge it open. There's some balance between blunting the crack and wedging it open, and there's some balance between water going down the crack and freezing. And if it gets too bad, what happens is not pretty. And so I make the labels go away, and then we make the ice shelf go away, and this is about 5 weeks. And after that, then this one sped up 6 or 8-fold. So you get, this does not raise sea level. I get emails on this occasionally. Professor, you should remember that ice floats. Melting ice shelves do not raise sea level. Please quit lying to people. Okay? But it got rid of this friction, and it got rid of this friction, and then this one can go 8 times faster. Okay, so yes, okay. And that can't do much to sea level because there isn't much ice behind it, but of course there's other places where there's a lot more ice behind it. And so realistically, for big sea level rise, if we don't have to worry about the ice sheets, life is easy. If all we're arguing about is thermal expansion in mountain glaciers, it's not very big. The big issues are Greenland melting on top and these melting on the edges and letting the ice fall in the ocean. And you've all got Greenland melting on top covered, so I'm going to tell you about this. So, okay. Now we've seen this elsewhere, right? So if you go to Greenland and you get in a plane and or a helicopter and you look in here, Connie Steffen's picture, you've probably all seen this one, but this is the beauty of Jakobshavn Fjord. Tundra over here, tundra over here. This has water underneath it, fairly deep water. The ice sheet is flowing towards you at the top, way in there. And if you fly in your helicopter up here, about there's a seal. And they're actually instrumenting these seals to do oceanography there because, man, getting instruments under there underneath otherwise is really hard. And eventually you get up to the front and there's a cliff. And the seal was down here in the ice fjord, and this is about 100 meters high, and the ice is flowing towards you from the left, and it breaks off here, and there's about 800 meters of water under that, and an 800-meter cliff on this side, with all kinds of fascinating things going on. Okay, so if we look down on this one, the next picture, there you go. So this is Ian Jockins, and the seal was down here. These are icebergs, the rock, the tundra up there and down there. The ice sat out here in 1992, and this was a flying buttress. That was the ice shelf, and the glacier was basically happy, and it was basically in balance, and it was one of the faster flows on the planet. And then this went away, and when that went away, this thing doubled to tripled its speed, and so it probably is the fastest flow on the planet. And what made it go away was 1 degree warming. And so this is Dave Holland's temperature profile in the ocean when the ice was happy and it had a flying buttress, it was stabilizing it. And this is the temperature profile out front in the ocean when the ice shelf broke off and it sped up. Probably 1 degree, no one has done this yet. I'm stepping out on a limb, but 1 degree is probably more than the ice shelves can take almost anywhere, almost any time. An ice shelf, you know, the Ross takes a few hundred years to go through. 1 degree warming takes 10 meters a year off the bottom. In 100 years, that's 1,000 meters. The Ross is not 1,000 meters thick. It's in trouble. And so 1 degree is a really, really huge insult to an ice shelf. There's some that will manage huge flows coming in and fairly robust, but think 1 degree is a big insult, and it took out Jakobshavn's. Okay, so that's sort of a scaling. 1 degree is a big deal. And you think about the waters of the world ocean, and most of them are at least 1 degree above the melting point, except the little puddles that hang around Antarctica and a little in the North Atlantic. And so this is a fairly big deal. I'm going to take you through a little tour of history here. I'm going to walk you into Heinrich events and show you that this warming has been influencing things in the past as well. And then I'll get corrected on some things later here probably. But at any rate, what I want to do, this is something that Martin Trufer sent me, working with Mark Fonestock, Ian Jockin. You have seen film of this from the Extreme Ice Survey, calving from the front of Jakobshavn. This is just a set of stills, but I want to show it to you. So, 100-meter cliff. Seal is down here someplace, iceberg, right? So this is a 100-meter cliff, so this is a big iceberg. And we're going to show you this iceberg rolling over. So it's just fantastic, you know? It's just, and that's a 100-meter cliff, right? So that's a 200-meter splash. It's just, and you can watch it displace what's in front of it there. It's just really, you know, we could just sit here and do this for a while. But in point of fact, you see a little bit of basal stuff and some dirt show up when it rolls over. And in fact, after rollovers, you often see dirty bergs out in the front. And that's the point I want to make here. What is an ice shelf? It is a flying buttress for the ice sheet, but it is also a debris filter. An ice shelf is a method to make sure that marine sediment core people don't find ice rafted debris. That's its main function in life, is to hold the ice against the ice sheet until the ocean has time to melt off the rocks in the bottom before it makes an iceberg. So if you go in front of the giant ice shelves of Antarctica, they have no rocks. The little icebergs, that are ice-rafted debris dropping in front of the Ross is primarily coming from little bergs that come drifting in from the side. There's no rocks in the bottom of ice when it has an ice shelf. And when the ice shelf goes away, then you can see the icebergs have rocks in them. Because you lose the iceberg immediately. It doesn't have time to melt off. It can roll over. Those can drift out. Now, at Jakobshavn now, it's got to go 50 kilometers before it can get out in the open ocean and do anything. But if Jakobshavn were out towards the shelf edge, losing an ice shelf would show up as ice-rafted debris out in the ocean. And so here's at least an interesting hypothesis. You go in the North Atlantic and you take a sediment core, and most of you know this, but this is going down, you know, 25,000 years or so in the sediment of the North Atlantic. And what you find in a sediment core of the North Atlantic is more or less the shells of small dead bugs, hunks of Hudson Bay. Shells of small dead bugs, hunks of Hudson Bay. Shells of small dead bugs, hunks of Hudson Bay. I mean, very, very crudely, that is the story, of course, in the North Atlantic, as they have these Heinrich layers that are ice-rafted debris that say all of a sudden a whole bunch of dirty icebergs got way out here, and before there weren't many icebergs, right? And so, you know, and this is stolen from Anne, and, right? And you either have small dead bug shells or you have ice-rafted debris, and they're fairly sharp things. And they sort of map like this. So the Laurentide is over here on your left, and Greenland is in here, and there's Iceland, and this is an isopac map of stuff coming out. And so in this contour interval is where you find hunks of Hudson Bay at certain special times in the past. Okay? And this drove me crazy for a very long time, because the hunks of Hudson Bay were a cold time. And I had just told you that warming is what attacks the ice shelves. And then along came Marcotte et al. And a little bit of data and some modeling, and they said, you know something? In the North Atlantic, when you make it really cold on the surface, the circulation looks a little more like the Arctic, and you get warm waters at depth. These intermediate waters spread north, and so they would get up, after a while, they would get up to the mouth of Hudson Bay, and then what happened? The ice shelf goes away, and you see that in the ice-rafted debris. And so what we're seeing is a story happening in Greenland, happening in the Antarctic Peninsula, happening in geologic history. When warm water gets to the grounding line, the shelves get in trouble. When the shelves get in trouble, the ice can go faster, and you see the effect. And so for cold ice, maybe the biggest single control is not sea level, it is not snowfall, it is the temperature of water at the grounding line. And the ice shelves of Antarctica are sitting in the coldest water on Earth for the most part. Okay? So that's really the issue. In fact, it may be that we see this operating in Antarctica as well. This is highly speculative. You don't have to listen to this. But, you know, the people that go looking for meltwater pulse 1A as we're coming out of the Ice Age, 14,700 years ago, there's this abrupt warming in the north. Sea level rise starts coming up like crazy, but that's probably just melting on top. But it looks like some ice came out of Antarctica. And it looks like it came out with an ice-rafted debris event. And circumpolar deep water is sort of modified North Atlantic deep water. And North Atlantic deep water cranks on nice and warm and going places at 14,700 to make that warming. And it's conceivable that we're seeing exactly the same story in Antarctica. The ice sheet retreated when warm water got to the grounding lines. That one's speculative still, but it fits in a general picture. Antarctica was biggest when it got the least snow. The less it snowed, the bigger the ice sheet was. Antarctica is not primarily controlled by snow. And it's fairly clear it's not controlled by sea level. It's controlled by the temperature of the water at the grounding lines. Okay, with fairly high confidence. So now let's go back here. We're going to look around here a little bit. Basically, everything in color on this map has the ability to make icebergs at some point. So it's sitting on a bed which is below sea level. And we normally focus over here because so much of the bed is below sea level and can make so many icebergs. Okay? And so that's where we're going to go. This is a long, different talk. If we had another hour, we'd go and do this talk. It is virtually certain that this ice sheet has gone away after it formed. And it's moderately clear that it went away during marine isotope stage 5e. So the last time it was warm, it's moderately clear that that went away. There is no smoking gun, single piece of evidence that shows that. There's a huge line of intersecting things that point in that direction. There's a real need for better work, but it looks like it's poised pretty close. It's gone away after it formed. It may have gone away really recently. And there's basically nothing that shows strongly that it stayed. Okay? So if we go in there, and let's focus in here. So this is what Terry Hughes and George Denton called the weak underbelly of the West Antarctic Ice Sheet. And here's some flow speeds. So this is basically that previous box with one coming in here and one coming in here. So that previous box. Black is screaming fast ice flow coming out of the ice sheet. Blue is slow ice flow. People have gotten done doing a lot of work on this one. It's worrisome, but it's not real worrisome. There's a fantastic, famous paper from Tad Pfeffer, and Tad sort of said, how much can the ice really speed up? And he said, you know, even you double, triple, quadruple the speed coming out, it's still not end of the world fast. There's sort of speed limits. And a lot of that sort of speed limit comes from the fact that the ice tends to sit in deep, narrow troughs, and there's friction on the sides. And it's really hard to take huge amounts of ice and run it out of a narrow hose. But this one, you'll notice that the fast flow, it doesn't just drop off like it does here, it fades off. And the fast flow actually goes way out to the sides. There's no deep, narrow trough there. If this one were it's huge. And that's why it's been identified for a very long time as being sort of the key thing. Huge amount of funneling of flow coming into this, and it doesn't have those deep, narrow troughs with friction on the sides that keep it from going really, really, really fast. The flow converges like that. Let me do this. I'll put those same flow over the bed, and what you'll also see is these holes back here are 2 kilometers below sea level. They're very, very deep. There's a sill right there that stabilizes it. The ice is funneling horizontally, it's funneling vertically. And it is held up on this narrow stabilizing sill. If it backs up, it gets to a place where it can dump more icebergs vertically and horizontally. And it gets to a place that has a calving front that is bigger than anything on the planet. All right? Now, if we do this, I'll turn that around like that, and I'll do the analogy. You know what happens at a merge. Okay? If this backs off the sill, Katie barred the door. And that's what Ian Jockin's paper said, was once you back off the sill, it goes really fast, and basically it goes. And that's fairly clear. You would retreat back here. Now, this is only Thwaites, but if it retreats back here and you try to stop it, there's a 4-kilometer high cliff. That's not going to work. So really, right now, there is worry. You may have seen a little bit of stuff that says that eventually we may get hot waters under some of these others, but it'll take some warming before we get there, probably. So attention is still mostly focused over here, although in a burn it all, make it stinking hot world, then you get worried about other things, right? So back to Ian, right? His result was, when we run our models for Thwaites Glacier, we find that the changes that have already happened in the ice shelf, if not reversed, will lead to retreat from the sill. There may be a century or two of slow change before it gets fast, and then it might get really fast. Okay, so that's the one. Now, right, loss is relatively modest over the next century, and then she goes. Now, we did something similar the year before, and we got a slightly different, Byron Perzak and a whole bunch of others, I'm way back here somewhere. But at any rate, this is part of the sea rise modeling effort. The data aren't quite as good as Ian's were. It's done a little earlier. They didn't have Ian's full set of data. But the models were simpler, and they ran a broader suite of parameter space. And what we found was that there were a couple of things that might allow it to be possible for this to still be stable. Maybe we haven't committed to loss yet. And the pieces that mattered in our modeling, one was, is this really a grounding line, or is it a zone? And how broad is that zone? Because if the warming can reach inland a little bit towards the inland edge of that sill, it can do damage a lot faster. And and we've been doing a lot of work on interesting things. People have been mapping ice shelves for a very long time and looking at them go up and down on the tides. And then they say, well, this is where the grounding line is, because that's where the up and down gets really small. But you know, if you've got tides taking your ice shelf down, there's no elevator right here. There's no giant fault right here. That if this goes down, this has to go up. And if this goes up, what's it going to do? It's going to suck water in. And so there is some tendency for these ice shelves to hurt themselves by sucking warm water farther inland. And we actually think we're seeing some evidence of this. So this is a very messy picture of the grounding zone of Willen's ice stream over on the Ross Ice Shelf. And there is, the floating part is right down here, and then there's a hydropotential low that will connect to the ocean at high tide that goes in here, and it may be running out here as well as running up here. It's not a grounding line, it's an estuary. And if it's an estuary, then if you warm the ocean, it can reach inland a little bit. And in our model, if you let it reach inland too far, it's not good. Okay. The other piece that was fascinating was the question about what is the bed? Where the ice is not yet floating, is it a fairly viscous bed, you give it more stress and it goes a little faster, or is it a plastic bed? You give it more stress and it goes a lot faster. And Ian only looked at a fairly narrow range of possibilities. Byron ran it all the way out to the end, and what he found was that if you make the bed plastic, the glacier can't really thin at the margin because it instantly reaches far inland to grab more ice. And it just manages to hold on to the sill if that zone of influence is not too wide. But if you make the bed viscous, then it's really not good for the long-term future. And the data basically say that some parts of the bed are viscous and some parts of the bed are plastic. And mapping that and putting it in right is something that we're not able to do yet. So there's a couple of knobs here that might still allow this to be just shy of the end of the world, but it's getting close, okay? So now let me show you the issue that comes up. My pictures of Jakobshavn I got during a remarkable adventure. I got on a plane with 10 senators and we went to Greenland. And so here's a picture of Senators Boxer and Mikulski in the ice fjord in Jakobshavn. And we got in the helicopter and we flew through here. And I can remember sort of saying to the pilot, don't get too much closer. And the reason is, okay, so this is a 100-meter high cliff, and you're all good enough to do this. That is close to breaking. Okay? It is. And you know, it's ice climbers know about this. Everybody, miners know about this, or quarry persons know about this. If you make a cliff that is too high, it breaks. And how high can a cliff be? This one suggests that 100 meters isn't too far off of that limit, okay? Now there's literature on this. It goes back to Holland in 1962, who said, you know, the ice always ends in a cliff and the cliff can't be too high. Hansen and Hook really looked at this in 2003. They came up with 100 meters as sort of the maximum cliff height for ice. And Jeremy Basis has been doing a lot of work on this since, and he keeps coming up with sort of 100 meters. Now this one at Jakobshavn is 100, and it's sort of tied with a couple others as the highest cliffs we know about on the planet right now, and they're sort of 100. Right? And so if this happens, at some point, if it maintains that cliff, it backs up off of the stabilizing sill, and the cliff is 200 meters high, or 3. But if the cliff can't be more than 100 meters high, and it's trying to get 200 or 300 meters high, what happens? And so like I said, you probably get much higher cliff, and that suggests that things are really bad there. So Dave Pollard and Rob DeCanto have this model of West Antarctica, and they took their model of West Antarctica, and they put in, once there's meltwater in the cracks, they said that will cause failure if the cliff is too high. And they ran it. Dave was trying desperately to explain the Pliocene. So if you remember, the argument on the Pliocene is it's fairly clear that CO2 wasn't much above what we are now, and sea level was a lot above what we are now. And it's really, really hard to do the sea level indications. There's a little uncertainty in them, but if they're right, it's really hard to do that with any model that fits the modern world. And so Dave was trying to find something else, and I said, Dave, put the cliffs in. And so he did. And it fixes the Pliocene. He now can take a model which works well in ice age cycling over the last million years, and it works well in other ways, and he can get the high sea level of the Pliocene without extreme forcing by putting in this extra piece of physics. But unfortunately, what it also does is means that once you get off of the stabilizing sill, whenever that is in West Antarctica, the time scale of getting rid of the West Antarctic, it's not centuries, it's multi-decadal. This is not maybe the best case, it's not the worst case. And so if this process happens and Thwaites backs up, it starts trying to make a cliff which is too high, and then it is a very worrisome thing. So you come back here, right? Did we just screw it up? We should give up, okay? Now the light piece, right? So the Onion says we're worried about the wrong things. Sea level could rise 1 foot or more if lots of people go swimming. Right? In fact, if you put everyone on Earth into the water, it's 1,000th of a millimeter. But okay, so that's not the big thing. Okay, so you know, what do we say? You look at warm times of the past. You look at stage 5e, you look at stage 11, you look at the Pliocene. We are basically committed to CO2 levels for at least a little while, which are associated with a lot of sea level rise in the past. Okay, and not with a time scale yet, because we don't have sea level histories with a time scale that really show what's going on. But you know, it's a lot could be in play. When Dave fixes the Pliocene in his model, he turns the temperature up, he gets that 3 meters plus 3.4 meters out of West Antarctica, but he actually gets sort of 14, 15, 16, 17 meters out, because he gets some East Antarctica too. And he gets that slower, but he gets it. And of course, if we make it really hot, you're putting another 7 meters in play in Greenland with fairly high confidence, okay? So the truth is, even if we have committed to West Antarctica going, most of the potential sea level rise is still not committed. Greenland is still not past its survival with fairly high confidence. The pieces of East Antarctica are still not past their survival with fairly high confidence. Most of the sea level that is out there is still in play. And if, for example, costs rise faster than sea level, a little bit is pretty cheap because we're used to it, and when it gets high, it gets really bad. If costs rise faster than sea level, the value of Greenland and the value of East Antarctica just went through the roof because West Antarctica is in trouble. So that's one thing we could look at. This is something we came out, Patrick Applegate did this, and a few of the rest of us, Byron's on there. And this is taking a fairly simple Greenland model and asking, what is the e-folding time for melting Greenland as a function of warming? And if you barely warm Greenland above the survival limit, this is 10,000 years. You can warm Greenland a tiny bit above its survival limit, hold it there, and it takes a really long time to melt. If you really crank up the temperature to some ridiculous level out in the future, 3 doublings of CO2 or something, the time scale for melting Greenland is under 300 years. Right? It is possible that Greenland got through stage 5 not because it was able to handle the temperature, but because the temperature went down real fast and it didn't get melted before it went down. So these things are still out there. And then there's also this stuff in East Antarctica. And it's pretty clear that these things at least partially deglaciated in the Pliocene from CO2 levels that are similar to where we are now. And 14 meters of global average sea level is in play there, right? So let me finish with a pretty picture and some penguins. West Antarctica may not have committed yet. If it is committed yet, it's Thwaites. It's very clear that it's happy with the Ross. It's very clear it's happy with the Filch-Nirani at this point. If there is, we're going down the tubes, it's Thwaites. Thwaites is very much a threshold system. As long as it sits on that stabilizing sill, not much. When it gets off that stabilizing sill, it could go fast. And fast may be decades. Right, this sort of, yes, we've got lots of time after it goes. It may be 4 meters from West Antarctica in the northern hemisphere in less than 100 years after it gets going. So for big problems, that's a big one. But after that, Greenland is in play. And pieces of East Antarctica, fairly clearly, if it makes it too hot, they also get in play. And Greenland is a lot more than West Antarctica, and the pieces of East Antarctica are a lot more than West Antarctica. So the real big sea level rise, even if we're committed, is still in the future. So I thank you for inviting me, and I'm sorry if that was chaotic, but thank you. All right, questions? Yes?
Has it been demonstrated that the ocean in front of Thwaites is warming?
Is it demonstrated that the ocean in front of Thwaites is warming? Sharon could probably answer better than I can, but there's a little warming in the waters around Antarctica in some of them. And there has been a notable change in the distribution of the already warm waters. And it's very clear that the shrinkage of the ice shelves in Thwaites and Pine Island and the speed ups in that area are related to the circumpolar deep waters getting up on the shelf and getting under there. So this business that right now is very, very crudely, the warm waters are below and at the edge of the continental shelf there. And if the winds change a little bit, they come up onto the shelf a little bit, and that's a big deal. And if they change a little bit the other way, they get below the shelf and they don't get to the ice. So they're at a very sensitive point right now, which probably is not coincidental, but at any rate. And then, so then it becomes maybe a little bit of warming in the waters, but mostly it is distribution of the waters. And that will be some combination of Natural variability, global warming, and the ozone hole. And I think at this point it's fair to say that all of those are potential contributors. None of them can be ruled out, and probably all three are involved at some level. That there's changes going on in the Pacific which are linked to, that are forced, as well as changes going on in the Pacific that are unforced, that are showing up as changing the water mass distribution by moving the wind systems, the Amundsen sea low and what have you, and that the ozone hole probably is tweaking the winds as well. Yes?
There's been some suggestion of volcanism under the ice.
Yes.
In that area, actually, near Pine Island Bay and so on. Does that worry you at all?
Right, so the suggestion of volcanism under the ice, and is that worrisome? Yes, there is almost certainly volcanism under the ice, at least recently and probably active in some places. And does it worry me at all? Not hugely. We were having a chat back here earlier about the water system, and if you focus melting in time and space, it tends to become less and less influential in changing the ice. So your tires have treads for a good reason. They want to take the water when you're out there and trying not to hydroplane and channelize it. And if you can move the water tightly in space, it doesn't do a lot. And so a volcanic eruption, what does it do? It makes a lake. The lake makes an outburst. The outburst makes a channel. The channel drains the surroundings, and you don't get a lot of lubrication because the heat melts the ice, and that favors channels. And if the water comes out in a channel, it doesn't do much. The secret to making ice unhappy is to spread the water out all over everything. And so it's not volcanoes as much as it is broad high geothermal flux that really matter for ice. And that's not likely to change much.
You do have a bit, I mean, the data aren't very good there, but...
No, so the data are, in terms of what's actually going on there, they're not. And I'll tell you, I mean, we have a student looking at this now, Nate Stevens, who's doing it for his master's, and he's writing the paper now, okay? So he's writing it, so don't scoop him. But, you know, he's looking at the question of, do these ice age cycles actually make it easier to have the volcanoes? And it turns out if you take your ice model and you look at the stresses in the flexing plate, that they are similar to the stresses needed to drive a dike if there's no buoyancy forcing and if there's no tectonic forcing just by themselves. And so it is conceivable that the volcanoes are there in part because the ice has come and gone. The Antarctic volcanoes are very interesting. They tend to be low melt fraction volcanoes. And something that made it easier to extract melt might favor low melt fraction volcanoes. So it's that's off to the side. That's not, the direct future and the near future probably is not a volcanic problem, but there's fascinating linkage to volcanoes. Yes?
Can you talk about the sea level rise that maybe is sort of overall predicted without the collapsing of the Thwaites ice?
Right, so Thwaites behaves itself. I think the projections are most of a meter this century if we continue on a burn a lot of it future, with rather low sensitivity to what we decide to do. We're already committed to some. The mountain glaciers by themselves are sort of 0.4 of a meter of sea level rise, and then they're gone. So melting mountain glaciers matters, but you know, sort of that gets us out of mountain glaciers with some uncertainty as to how you count the little things around Antarctica and around Greenland, because there's a whole lot of ice hugging up close to the big ice sheets that sometimes gets counted with them and sometimes doesn't, and some of that is whether you're doing imagery or whether you're doing grace gravity and things like this. So there are issues that come into resolution, but overall not more than 0.5 meter or so from those. Thermal expansion is I forget the number. It's some fraction of a meter per degree for the ocean warming. And, you know, the whole ocean temperature change from glacial maximum to today was probably only a couple of degrees. So the thermal expansion term it matters, but it's not huge. So realistically, sea level is somewhere close to a meter this century if the ice sheets behave themselves. And then there's this delta we don't know yet. And in the 2007 IPCC, we gave quantified numbers excluding future rapid dynamic changes in ice flow. We don't know what they're going to be. You pick a number, add it to it. In this one, they're back to actually giving numbers, but what this talk basically says is that we had it right 2007, which is they've got a very nice quantified future done properly, and then there is some slight chance that we blow the top end off of that. And the best estimate for the mid-range, I'd still go to the IPCC. I'd take their number. But if you drew the uncertainty curve, there's a number, or a little less, or a little more, or a lot more. And there's no lot less. So, yeah, so back, yeah.
What kind of data would you like to have more of, especially, I guess you mentioned profile temperature data, but
Yeah, so we would love to know more about the ocean around there. And we would love to know more what about the ocean can do running into the future. Because anything that moves that cold water is bad news for the ice. And then we would, self-serving, this is not independent warning, we're putting in a proposal to try to do this. So we would love to know more how much stabilization is left on Thwaites from the ice shelf. We'd love to know more the details of the topography underneath it and the bathymetry out front. We'd love to know, are there channels that cut through that ridge that would let water have access? We'd love to know, are there puddles of till that make part of it plastic, or is it all viscous? And then data on the real details of what is going on, so that we hopefully could use the signal of the evolution of the ice to constrain better what is holding it back underneath. So really using all the tools that glaciology has built, focusing on the most dangerous outlet would be that. And then, and with some of this has to go to glaciologists, but a whole lot of it should go to oceanographers. I'm sorry, Dad.
I was interested in your ice cliffs, and I didn't, the 100-meter limit to the ice cliff height, I didn't quite understand how that affected Pollard's model that made it work. What was magic about that limit, number one. And number two, if I can squeeze in two, is what sets that 100-meter limit? Is it fracture density or inherent strength of the ice?
So the question on this 100-meter limit, what sets the 100-meter limit is basically the inherent strength of ice. And it's with a couple of asterisks about you get close to the grounding line and there's almost always pre-existing flaws. And so all of fracture mechanics is this world of we have a material, and the material in a pure, perfect state is incredibly strong, and everything in the world fails fantastically earlier than it's supposed to. And back in the dark ages when I was taking metallurgy at Wisconsin for my minor, I had a prof who'd come in with broken things. And he'd show us broken things. The pilot survived this. It's a strut or something that had broken through. And at some point he said, you're going to calculate everything to 5 significant figures, and you're going to build it 3 times stronger, because no one will ever believe you got it right to a factor of 2, right? So this 100 meters is fuzzy in that sense, because there's some assumption about flaw distributions and what have you buried in this, and it'll look different in different places and for different forcings, and Jeremy has got a lot more on this. But with that, if you put in a cliff that's too high, fails. Once it retreats and gets a cliff that's too high, it fails. And so you get very rapid retreat. And so in the modern world, Ian Jochen, for example, had this paper on Jakobshavn in 2011 that we looked at, that I helped just a tiny bit with. And what you see at Jakobshavn is it will break off to a point where it's not very close to floating. And then it stabilizes there until it thins to very, very close to flotation, and then the next piece breaks off. And that's because when it's notably above flotation, it's held down at the bottom, and it has friction with the rock, and it's really hard to break off that first piece because it's there. If the top fails, so if you get a cliff that is high enough that it fails spontaneously, the top goes off, there's nothing holding down the bottom, and the bottom comes off. And so then, and like I say, I don't think, Dave has parameterized his in interesting ways. My suspicion is that the physics would get really nasty, and that in fact 100 years is an overestimate. And probably the physics would turn into jamming in the forefield. And so melange is holding the thing up. But just the basic idea, everywhere and every when, ice that is floating or close to it ends in a cliff, right? Ice on land, a whole lot of it ends in a ramp, and ice that's floating ends in a cliff. Because if the top falls off, then the bottom isn't held down and it comes up. And if the bottom falls off, the top is not held up and it falls down. And if you notch it at the water line, they both fall off. And so, right? So there's this inherent instability that in a floating ice mass, the top holds the bottom down and the bottom holds the top up. And either one of them goes, the rest of it goes. And so if you get a cliff instability on top, there's not much to help you.
The ice can't get out of its own way fast enough.
Yes, that would, and probably that's the answer, is it wedges in the mouth there and you get this giant ice melange that wedges in. But if you're counting on that ice melange to stabilize West Antarctica, my guess is it's a short time. Yeah. Yes?
You explain this better than anybody. The senators get the message.
They haven't asked recently, but at the time we were doing it, I think most of them did. So it was, and this is, you know, you get on and this is a few years ago, 7, 9, something like that. But you close the door, and there's no reporter, and the senators turned into very interesting and very interested persons, and they tell jokes, and they talk to you, and they ask questions, and they're putting it together, and I was very impressed. And you open the door, and the press is there, and they start reciting lines they've memorized. And part of it, if you wanted to put this in a good light, you'd do it this way. Eventually, they will stand for re-election. And if you say 1,000,000 words that are right and 10 words that are wrong, the 10 words that you said that are wrong are going to be used against you 1,000,000 times. And a misstatement is fatal in the modern world. A very interesting mess. And nobody is smart enough to make clever answers in real time and know not only not to say anything wrong, but know how their words could be taken out of context. Right? There's this fantastic quote which is attributed to Cardinal Richelieu, although it's probably a little younger than him, which was, and it's a time when they would have been gender specific, but nonetheless it says, "Give me 6 lines in the hand of the most honest of men, and I will find something in them that I can hang him with." Right? So when the door is open and the cameras are rolling, they tend to go to script. My personal opinion is that many of the senators are among the most frustrated human beings on earth right now, because what is going on is bigger than they are. Yes?
Science, sorry. I was wondering, in that kind of model, when you see the time scale of Greenland ice sheet loss move from thousands to hundreds of years, do you have a sense of what the rates of loss look like over that period? And as you're getting a smaller total time period, are you just smashing those rates into that shorter period of time? Or is the kind of profile of what those rates look like across that period?
Yeah, there tends to be a little incubation, and then it goes really fast, and then there's a little tail when it's stuck with little mountain glaciers up on the mountains there on the east. But it tends to plunge pretty fast.
And probably either way, whether it's over thousands or hundreds.
Yeah, and Patrick's got that somewhere in the paper. We could pull it out later. So, and that's not, that's not in any way a sophisticated model. This is Psychopolis, right? So it's a perfectly fine shallow ice model doing perfectly fine things, but sort of you have learned things that are not in that model. Okay, so in that sense, there's tweaks that you could make to it. It tends to be a little steep on the sides, and so there's some things like that may change the numbers a little bit. But the basic idea that when it's just barely above melting, it takes a long time, and when it's way above melting, it goes really fast. That's basically right. So how far we, in terms of rates of sea level change, we will decide how fast Greenland goes. Or we will decide not to decide, which is deciding. So yeah. Sorry. Yes. Yes?
Do you, I mean, barring, the information so far that you're hoping to get from the proposal you have in, what sort of uncertainties or bars do you put on place in reaching that threshold in Thwaites?
Yeah. I mean, that's the question, right? And threshold systems are such a pain for this very reason, that if it just hangs, I mean, you look at you take a ship and you get your side scan sonar and you look at any deglaciated shelf you can think of. And there are very few deglaciated shelves that you can actually see these annual retreat moraines, probably annual, that it's pausing every winter when the sea ice packs in or something like that. But almost all of the shelves, what do you see? There's this big grounding zone wedge. And some of them are steeper and some of them are flatter, but they're the ones in the Ross Sea are thousands of years of sedimentation. And then there's nothing. And then there's another grounding zone wedge somewhere way up there. And so it sat for thousands of years, and then went whoop. And there's all these stabilizers. If you're trying to float it off just slow enough, the sediment will get in underneath it and it'll help. And if you're drawing down the inland a little bit, you're reducing the self-gravitation, and that drops the sea level next to it a little bit. And if you're thinning it slow enough, then the land underneath is rebounding a little bit, and that's helping you. So there's all these stabilizers that are sitting there so that it hangs on, it hangs on, it hangs on, it hangs on. Oh my gosh. And that's and how fast the oh my gosh is not recorded, but it didn't pause. It went from here to there without pausing long enough to leave a record. And so what the data say is that the Antarctic has lived as a threshold system on these. And it's typically lived, it doesn't look like the different wedges are always synchronous, so some of it may be that this drainage goes at one time and this drainage goes at another time, but the dating sucks, right? So it's hard. And so what you put on are the uncertainties are almost nothing from this, or really huge with not much in between. It's one of when the most recent National Academy report on abrupt climate change that Jim White chaired basically said, a lot of the abrupt climate changes we were worried about from the physical system seem to be pretty well buffered. They won't happen. A lot of the abrupt climate changes we were worried about in biological and human systems are still worries. But if you were to pick a physical system that might still have threshold behavior, you'd probably start with Thwaites Glacier in West Antarctica. Yes?
So a little bit on that, is there any interaction/feedback between losing ice and the change in sea level, the fact that your early slide showed that you actually drop sea level close to West Antarctica?
Yeah.
Is there any interaction there, or it's completely different?
I think that is one of the reasons why the ice tends to stabilize for very long times at particular places. So my suspicion is that is in there as a stabilizing feedback. But if the sort of changes that have been happening recently, the ice sheet gravity is sort of integrated over most of the thing. And the change in attraction for the ocean water that happens in these near coastal changes is not very big. And so that's mostly going to be a slow stabilizer, even though the direct influence of gravity attracting the ocean is real fast. But because most of the mass is doing the gravitational attraction is inland, and the time to propagate inland is slower now, it's a slow stabilizer. So it's a stabilizer, it's turned on, it's working, but it's probably not terribly important. Anything else?
All right.
Okay. So thank you. Thank you.